Thermodynamics is the study of heat conversion to other energy forms. But for this grade, I'm going to talk to you about the heat conversion into mechanical energy. But this thermodynamics chapter studies the heat conversion to any kind of energy. But for your grade, you're going to learn only the heat conversion into mechanical energy. So I'm going to focus on the mechanical energy part. Mechanical energy. Now we have said that thermodynamics is the study of heat conversion from heat energy to other form of energy, specifically mechanical energy. So there are terms that you have to understand in this chapter. The first one is mole. The second one is molar mass. The third one is temperature. And the last one, as you guessed it, the fourth one or the last one is heat. You have to define these terms. Well, mole is just a number, the number which is equal to 6.02 times 10 raised to 23. 1 mole is just a number, just like when you say 1 kilo is just like 1,000. 1 mole is this amount of anything. I mean, it could be other molecules or anything. Molar mass is the mass of a molecule associated when the number is 1 mole. So molar mass is the mass of a molecule. Is a mass of a molecule at 1 mole of its constituents. Now we have defined molar mass. Now let's define temperature. Temperature is the average kinetic energy of a particle. So it is the average kinetic energy of a substance. So it is the average energy. But when it comes to heat, heat is the total kinetic energy or the total kinetic energy of a substance or a system. The two are very different. These two are very different. Well, we're going to discuss it. We're going to discuss their difference later on. Now we have defined the temperature. Let's talk about the first law of thermodynamics. Well, the first law of thermodynamics is actually another word for the law of conservation of energy. It says that the first law of this says that energy is conserved. In short, the first law is actually a restatement of law of conservation of energy. It says that energy in a isolated system is conserved. This has an implication, mathematical implication. I'm going to write it now. I'm going to delete it to make more space. Okay, I'm going to draw a picture here. Assume that this is a cylinder, and in the cylinder there's a piston, just like this, and inside this cylinder there's a gas molecules. Now, before I tell you about the mathematical implication, I have to define two things: the system and the surrounding. A system is a body which is subject of the study. So in our case, the subject of the study is the gas. A system is just any body which is subject of the study. So in our case, we are studying the property of the gas. And the surrounding is anything that applies or influences the system. So in our case, the surrounding will be the piston. So this is the surrounding, and this is the system. So the first law says that if the system is isolated, then its energy cannot go anywhere, or another energy is not added to it. So this is the restatement of the law of conservation of mass. Okay. Before I write the equation, I'm going to define what internal energy is. Internal energy, as you guessed it, is the energy associated, the total energy associated within a system. So in our case, the gas. So the total energy associated with the gas. But total energy includes the potential energy plus the kinetic energy plus nuclear energy and so on. But in our case, we're only going to study the kinetic energy part, which is associated with most as internal energy. Actually, this is thought of as an ideal gas. So when you consider a system that it is an ideal gas, or when you consider this gas as an ideal, then the potential energy and all those energy associated will become zero, because they don't affect the property of the gas unless it is subjected to very high energies, just like the temperature and the pressure of a sun or a star or a nuclear reactor. So now we have defined the internal energy as the total energy associated within a system. Now we can easily write it as, we can easily write the first law of thermodynamics using formula. Okay, now we have defined what internal energy is. So it is very easy to define it using a formula. So now I'm going to write the internal energy as U, which is symbolized. I'm going to symbolize it as U. The internal energy is the heat supplied to the system, the heat energy supplied to the system. So I'm going to write the heat as Q plus the work done on the system. So I'm going to write the work as W. So now the internal energy is given by this equation on. There's a difference why I write the work done on. If it is work done by the gas, then the work will be negative, so the internal energy will decrease from the heat supplied to it. If heat is supplied to the system, then Q becomes positive, and if heat is taken away from the system, then Q becomes negative, so the internal energy decreases. Okay. Now, but the work, if work is done on a system, that means work means any mechanical work. So you're going to associate it with the mechanical work done on a system. So if you do a work, if you, for example, compress the gas with using the piston, then the work is done on a system. So the work done on the system will become positive. But if the gas expands and does a work, then the work will be negative, so the internal energy of the gas decreases. I'm going to tell you the application of this in the later parts. Okay, now we have talked about the first law of thermodynamics, which is changing internal energy is equal to the heat supplied to the gas plus the work done on the gas. Actually, this formula can be rewritten as U equals Q minus W by. If work done by the if work is done by the gas, then the internal energy decreases. So that's why I added negative sign. But if work is done on the gas, this WBY becomes negative, so negative times negative becomes a positive. So the positive will add with this Q, and the change in internal energy will be will be higher or increase in this case, in our case. Before we go to the zeroth law of thermodynamics, I'm going to tell you about thermal equilibrium. Now, thermal equilibrium is just a condition whereby if, for example, you have two bodies having different temperature, let's call this A and let's call this body B, and if this is at 100 degrees Celsius and this body is at 10 degrees Celsius, and if you connect the two, if you put them side by side like this, where there is a contact between them, then the heat will flow to this side. Then they'll become at equilibrium. So heat is going to flow until they are at the same temperature, but not at the same heat energy. If For example, let's call this, it is a 10 kg and this is 1 kg. If you contact each other, if you make them touch each other like this, then the heat is going to flow, not the temperature. Temperature can't flow. The heat is going to flow to this side, to the B, which is a colder one, from a hot source to the cold source, until thermal equilibrium is reached, but not the energy equilibrium. The energy on the two bodies can't be equal. When I say energy, I mean the internal energy. The internal energy between the two bodies can't be equal, but the temperature will come to a thermal equilibrium. So A and B will have the same temperature, but they cannot have the same internal energy, because the higher mass has the higher internal energy, because internal energy is dependent upon the mass of a gas. So if they are in thermal equilibrium, there is no net heat exchange. Now this law is very important because it allows us to calculate or measure variety of temperature. For example, assume that this is a mercury thermometer with a bulb like this, and there's a mercury in here. So it's going to rise like this to this, and it allows us to measure the temperature of a system. Let's say this is a 50 degrees Celsius water. We put it in a 50 degrees Celsius water. When you put a temperature measuring device, this mercury barometer, a thermometer, the thermometer is going to read until the mercury is going to rise to the cylinder until thermal equilibrium is reached. So when thermal equilibrium is reached, then you can measure the temperature, because the two bodies will have the same temperature. So this will give you an accurate measurement of the temperature. But if the mercury is rising, and hasn't stopped, then you cannot take the measurement where the mercury was in the previous position. So you only can measure when the rising mercury stops rising or stops moving. But unless and otherwise, you cannot have an accurate measurement. If you put a measurement like that, you're going to have a lot of trouble and inaccuracies associated with your studies. So that's why this thermal equilibrium concept is very important in also measuring devices. For example, I'll give you another example. Let's say this is a temperature probe or thermometer probe, and you want to measure the temperature in, for example, a nuclear reactor. Let's assume that this is this is the place where nuclear reaction takes place. So the temperature is very high. So when you probe this in here, if the temperature just rises, you have to wait until it is steady or it comes to a halt. If the temperature doesn't rise anymore, or the temperature comes to a halt. Unless and otherwise, you cannot measure the temperature at this stage, if it is rising or if it is falling also. The same applies if you are measuring low temperatures. If it is falling and hasn't stopped, you cannot measure the temperature. The temperature has to, the measuring device has to stop rising the value or decreasing the value. of what is to be measured. So this concept is very important. Another law of thermodynamics is the zeroth law of thermodynamics. This law states that this law, the zeroth law states that if you have two bodies, let's say A and B, and there is a third body called C, such that it is in thermal equilibrium with both of them, with both A and B, then you can say that A and B are at thermal equilibrium. I'm going to delete this. Okay. Now enough of this property is actually like the transitive property in mathematics. For example, if A is equal to B and C is equal to also B, then you can say that A and B are equal. This is just saying, just like that in mathematical properties. Okay, now let's come to temperature scale. In temperature scale, there are three types of measurement that you can use, but the standard one is the Kelvin. There is temperature in degrees Celsius, there is temperature in degree Fahrenheit, and there is the temperature in Kelvin, which is the standard unit of measurement of temperature. Now, in degree Fahrenheit is 9/5 times temperature degrees Celsius plus 32. In Celsius scale is I'm writing the conversion scale, the conversion of the three. Degree Fahrenheit minus 32. To know the temperature in Kelvin, you just have to add degree Celsius with 273.15. Okay. Now you can convert the three just like this. Okay, now let me delete this one. Okay. Now enough saying about this. Now I'm going to talk to you about the absolute zero. Absolute zero. This absolute zero is a concept that at temperature Kelvin equal to 0, at when the Kelvin scale at temperature, like when the Kelvin is 0, all matter stops moving and all the internal energy will become 0. So this means that the internal energy of an object will become 0. That means the object will have no kinetic energy and also a potential energy and other energies and other energy associated with it. So, in a sense, which means that a substance ceases to exist, or the matter ceases to exist. That's why, although we can reach about 0.01 and less at very high freezers, we cannot reach at absolute zero, because if we do so, we're going to break the law of conservation of mass and energy. So that's why scientists are still trying to break that law. Okay, now I'm going to talk to you about the phases of matter. You know from elementary school that there are 3 phases of matter, or from grade 9, the 4 states of matter, or 4 phases of matter. So first, let's define what a phase of matter is. Phase is just a point at which or where the index of refraction and the physical properties of a substance doesn't change. Now, what is a point? Well, a point is just a point just means that at specific temperature and specific pressure. So phase is just a point meaning the temperature and pressure at which the index of refraction and the physical property of a substance doesn't change or is uniform. When you talk about a phase, it's very important to include those two. Those are temperature and pressure. Those 2 points are temperature and pressure. So now take for example, simple example of water. In water, we're going to have this. Just assume that the water in it is in a beaker. Let's call this at room temperature, or 20 degrees Celsius, which is room temperature. At 20 degrees Celsius, the physical property of the water, let's say that it is pure distilled water, so it has density of 1 gram per centimeter cube, or per milliliter. So, the density of water at 20 degrees Celsius is 1 gram per centimeter cube. So now the beaker is open. We know that atmospheric pressure acts on this water, so it will become 1 atmosphere. So now the phase of water at 1 atmosphere, which is and at 20 degrees Celsius, so see the 2 points, the pressure and temperature, they are a point. So at 1 atmosphere and 20 degrees Celsius, the density of water is 1 gram per centimeter cube. So the phase of the water is liquid at 1 atmosphere and 20 degrees Celsius, and the index of refraction is, I think, 1.3. So this doesn't change. So a phase is just a specific temperature and pressure where a substance exists in which their physical property is uniform. So if for example, if you take 1 atmosphere of pressure and act on a water and raise the temperature to 20 degrees Celsius and take it to Mars, the water is still liquid. The phase doesn't change. So the physical property doesn't change. And if you take the same substance on the Earth, it is still going to be, the density will going to be 1 gram per centimeter cube, and index of refraction will be 1.33. So the phase is just a specific temperature and pressure at which the physical property of a substance doesn't change. So this is what a phase means. Now, there are 4 phases of matter. The first one is liquid, as I told you. Liquid. Second one is solid. And third one is a gas. And if you ask, the fourth one is just a plasma. What is liquid? Liquid is a phase of matter in which the matter has a volume but has no definite shape. But when it comes to solid has definite shape and definite volume. This is compressible. Solid is very hard to compress relative to liquid. But when it comes to a gas, this is very compressible, and this has no definite volume and a definite shape. And when we talk about the volume, that it can be compressed into a tiny box so that the gas has a very high concentration. For example, take oxygen or hydrogen. You can compress both 10 liters of this gas into 1 liter container. But you cannot put 10 liters of liquid in just 1 liter of container. That is the difference between the two. Gas can be compressed so that if you take, for example, 10 liters of oxygen, you could just compress it into 1 liter of bottle. Or if you take any gas, this can't be done so, unless the gas condenses. So that is the main difference between that. But when it comes to plasma, it's just supercharged state or superheated state of a gas. For example, this plasma actually forms at temperature beyond 10 raised to 4 degrees Celsius or Kelvin. You can take one of the two. If the temperature is above 10,000 degrees Celsius, then this plasma forms. This plasma actually is very important for example, in metal industries and smooth cutting in metal industries and precision cuttings, because this thermometer is so high in temperature such that it can melt any metal. Even tungsten melts at 3400 degrees Celsius, the most temperature resistant material known to man. So at this temperature, this is going to boil it, so it is very easy to cut metal at this temperature or using a plasma. Going to delete this. Now let's talk about the curve. Of phase of matter. Just assume that this is an XY graph. This is the y-axis, this is the x-axis. The y-axis shows the pressure and the x-axis shows temperature. So now I'm going to draw a curve. Excuse me. to define each of these points. This point, and this point, and this point. What are these called? And so on. This point is called the triple point of a substance. Triple point. It is a point where the three phases of matter exist. This is temperature, and this is the pressure. Pressure at triple point. So triple point is a point at which the three phases of matter exist. Actually, this is the solid. This is the liquid, and this is the gas. So this curve shows that the turning point of a solid to a gas, or sublimation curve. This is called a sublimation curve, and this is called a fusion curve, in which is a point in which the solid turns to liquid, or just melting curve. Its another name is melting curve. And this is called vapor pressure curve. Or boiling curve. Now this point is called the critical point. Critical point. And this is called the vapor pressure point, or the boiling point. And this is called the sublimation point, in which the solid turns to gas directly, or the gas turns to a solid. So this is a sublimation curve, and this is called fusion curve, in which, or a melting fusion or melting curve, is a point at which solid turns to gas. No, I mean liquid. And this is called an evaporation curve or boiling curve. It's a point at which a liquid turns to a gas and vice versa. Most substances have this kind of phase curve, phase diagram, or phase diagram. This is called the triple point. This point is a triple point, and this point is a critical point. Critical point is a point at which the liquid phase, and the gas phase doesn't have a definite points, or they don't have a definable point. So it's just a point at which the two phases exist, but it's hard to determine which is which. This point is above the critical curve. This is called the supercritical curve, which is just another exaggerated form of the critical point. And the material above the critical point is called supercritical fluid. So a substance below it's a substance that exists if the temperature and pressure is below the curve of the sublimation curve and below the curve of the boiling curve, then the substance will most likely be a gas. and a substance has a pressure above the sublimation curve and a temperature below the sublimation curve, then the substance will most likely be solid. And if substance has a pressure above its boiling curve and a temperature lower than its critical point, then the substance is likely to be a liquid. A triple point is a point where the three phases of matter exist. Almost all substances follow this curve except water. Water has actually a negative slope, just like this. So the liquid phase, so the slope is just like this. So which means in case of water, you're not going to have a curve just like this. So water has a slope just like this. So that's why it's still debatable to talk about the properties of water. Actually, the triple point of water is triple point of water is triple point of water is at 273.16 Kelvin and 0.01 atmosphere. You can correct me if I'm wrong. Okay. I've talked about the internal energy and the sign of the two. Now let's talk about work done on a gas. How do you calculate the work done on a gas? Well, work is defined by the force times the displacement, or F dot S for that matter, or F dot product of displacement. But you see here that there is no displacement and there is no force. There is a force and there is a displacement, but you cannot calculate using these terms when you're talking about the gas. When you're talking about the gas, you use pressure and volume. So, but a force is equal to the pressure times the area. So from this, you calculate the pressure is equal to the force per area. Now you substitute the force with pressure times area. So the work becomes the pressure and the area times S. But S is the displacement of this piston. So you know that A dot S is just the volume or the changing volume of the system. So the work will be calculated as pressure times changing volume. So to calculate the pressure, to calculate the work done by a gas or on a gas, then you have to know then you can calculate the work done using this formula. So from the previous example, or from the previous law, or the first law of thermodynamics, you know that the internal energy, or the change in internal energy, is the the heat energy added to the system minus work done by the system. Now you can replace the work done by the system using this formula. So the internal energy will be equal to heat added to the system minus the work done by the system. I'm going to delete this one from cycle space. Now, enough of being said about the first law of thermodynamics. Now, let's come to thermodynamic process. Now, a thermodynamic process is actually a process in which the phases of matter exist, in which when the state of the system changes due to change of variables such as temperature or volume, is time. So, thermodynamic process is a process in which there is a change due to change in variables like temperature and pressure. The thermodynamic process is a process in which its states, when I tell you about the state means temperature and pressure of the gas or the system. So there are four types of thermodynamic process. The first one is isobaric process. Isobaric. The second one is isochoric or isovolumetric. The third one is isothermal. Fourth one is adiabatic process. This for our thermodynamic process. In isobaric process, iso means the same, so baric means refers to pressure. So it's a change in where the change is only in volume of a gas or a temperature of a gas. So in isobaric process, there is no change in pressure. So isobaric means no change in pressure. When you say iso, it means the same. So volumetric means volume. So there is no change in volume. In isothermal, as an answer justice, it means iso means the same. Thermal refers to temperature. So it's a process in which the temperature doesn't change. Whereas the adiabatic, all the three things change. The temperature, the pressure, and the volume changes. So let's start each of them using the first law of thermodynamics. Now from the law of thermodynamics, in the first one, which is isobaric, the pressure stays constant, the work done is equal to the pressure times change in V. So the work done by the gas, which is equal to P times change in V, pressure doesn't change, so the work stays the same. So the change in internal energy is the heat added to the system minus P change in V. So now there is the process. Now if you draw it against the pressure versus the volume, the isobaric process will look like this. It is a horizontal line. The volume keeps changing, but the pressure doesn't change. So this is isobaric process. This process can be achieved by adding heat slowly at constant pressure. So enough talking about this. You could have a calculations based on this, but I'm not going to talk about that in this video. Okay, let's come to the second part, which is the isochoric or volumetric. Now, this takes place at constant volume. So in this process, the volume doesn't change. So change in V becomes 0, which means that from the work, which are the formula P times change in V, if the V is 0, the work becomes 0. So these are the graph shown. The PV graph of this process is shown like this. So now the volume doesn't change, but the pressure may change. So in this process, the work done is 0. So the change in internal energy will be equal to the energy added or lost to the system, or by the system. Okay, now let's come to the third part, which is isothermal process. Let's delete this. In isothermal process, isothermal process. In isothermal process, the temperature doesn't change, so change in T will equal to 0. So now if change in T is equal to 0, then the internal energy doesn't change, because internal energy, which is a change in internal energy, depends on temperature. So if the temperature doesn't change, I have told you before that the internal energy is the sum total of the potential and the kinetic energy of a system. Now, for our sake, we put the potential energy to be 0 to is the calculation for our grade. So potential energy is 0. Now the only thing left to be the internal energy is the sum total of the kinetic energy. Now the kinetic energy of the system, if the temp, which is the kinetic energy of the system, which is determined by the temperature. So if the change in internal energy is the change in the total kinetic energy of the system, if the change in temperature, the temperature determines the kinetic energy. So if this change in temperature is 0, then the change in kinetic energy will be 0. So the internal energy will also become 0. So in our case, then the law of thermodynamics can be rewritten as Q minus W by. So you could take W by to the other side. This is actually 0, so W by is equal to W by is equal to Q. So the work directly does a work. The work is directly changed into heat. The internal energy of this system doesn't change, and it has a graph shown like this. If this is the temperature, the volume, and this is the pressure, then this has a curve just like this. This process is actually this process has to be extremely slow such that to achieve this thermal equilibrium process, because it's very hard to do that. For example, this process takes place when, for example, when you reach the boiling point of a liquid, for example, water. Until all the gas have evaporated, the boiling water will be only at 100 degrees Celsius, not more nor less, but it will be at 100 degrees Celsius. So at this point, this is the isothermal process. When you boil water at this temperature, if the temperature doesn't increase, the boiling point of water is 100 degrees Celsius, and if you put a balloon to it, then if there is a balloon and if you boil water in which the gas molecule doesn't escape this container, then the rising steam will have an effect of inflating this balloon. So the temperature of the liquid stays the same, which is 100 degrees Celsius, and so is the gas. So in this process, just the heat energy does a work. In this case, the heat energy, which is supplied from the heat source, is directly converted to the work. But this process is not the 100% of the heat energy supplied is not changed into work. We're going to discuss the reason later on why that can't happen. You cannot change the heat supplied to a system to 100%, the 100% of the heat supplied to a system into mechanical work. I'm going to discuss it at the second law of thermodynamics. Enough saying about this. Now let me delete it. Okay. Now let's come to the third part, which is the adiabatic process. In adiabatic process, both three things change. In adiabatic process, both three things change. So in this process, both the temperature change, the pressure changes, and the volume changes. So, but in this process, heat is not added to a system or taken by a system. So it is a process in which there is no transfer of heat, in a sense. So it means that this system doesn't transfer heat energy. So which means the change in Q is zero, or heat is not added or gained or lost by a system, which makes the internal energy, change in internal energy, equal to the work done by a gas or on the gas. So the internal energy does a work, and the work increases the internal energy. This is a very important formula because almost all engines work using this formula. Another process I will talk to you about is the cyclic change. Cyclic process is a process in which the process returns to its original position. But before that, let me draw the graph of the adiabatic function or adiabatic process. This is the pressure, this is the volume, then it will have a curve like this, like the isothermal, but the slope is higher in this curve. The curve of the slope is higher than the adiabatic one. Okay, now I'm going to delete this one. I'm going to delete this. Now let's write the work done at constant pressure. Let's compare the three processes: the work done or the heat and the internal energy in the full process. Now let's talk about the isobaric process. In isobaric, change in U will be equal to Q minus W By, which is work done by a gas or by a system in isobaric process. Actually, I'm going to write it isobaric. Change in P is 0. In isochoric or isovolumetric, change in V is 0, which means the change in U will be equal to Q, because WBY is 0. In isothermal process, then the change in U is 0, so the Q is equal to the work done by the gas. In adiabatic process, and the change in U will be equal to work done by the gas. And now in isobaric, the pressure is constant. In isochoric, the volume is constant. In isothermal, the temperature is constant, or the PV is constant. In adiabatic, the Q is constant, or the Q doesn't change. So this is the main difference between the four processes. And now let me delete this picture because you don't need it anymore. So now I'm going to talk to you about why the isothermal process, the PV is constant. You know from the ideal gas law that PV is equal to nRT. Now from this ideal gas law, you know that N is constant for a system because the gas is in a container and can escape, so the N doesn't change, which is the number of mole. R is just a constant, which is equal to 8.3, I think it's kilojoule per mole, or as a value, and R is constant. So if T is constant, if this T is constant, then the PV is constant. So, but each individual P and V are changing, but the two, the multiplication of the two is constant because the temperature is constant. Okay. Now in adiabatic process, the only constant is changing Q. In isochoric, the volume is constant, so the work done by the gas or on the gas will become 0. So the internal energy is turned into heat, or the heat increases the internal energy directly. Okay, now I'm talking about the fourth process. Now let's talk about what molar heat capacity is. You know from your previous heat and temperature courses that you know what heat capacity is. Heat capacity is the heat required to raise one amount of substance, or an amount of substance to raise by 1 degree Celsius or 1 Kelvin. The heat energy required to raise the substance by 1 degree Celsius is known as heat capacity. But when you call it molar heat capacity, is the heat required to raise 1 mole of a substance by 1 degree Celsius. Now the molar heat capacity means, which is is given by CV and CV change in T. Now when you call it the heat capacity, then it is known as M. From lower grade you remember that M, C change in T. Now the two has similar structure. Now when you say specific heat capacity, you mean that the heat energy required to raise a kilogram of a substance by 1 degree Celsius. But when you talk about molar heat capacity, you talk about the number of moles of the substance. So it is the heat energy required to raise 1 mole of a substance by 1 degree Celsius. And this is the constant. The molar heat capacity constant is known as CV. CV is the molar heat capacity of the substance at the same volume, or if the volume doesn't change. And this is just as any